Okay, these are going to be our notes about inverse trigonometric functions, often referred to as inverse trig functions. When we want to find the inverse of a trig function, meaning a function that undoes a trig function, we've got a problem. Because trig functions in general are not one-to-one, so for example, if you look at their graphs, they will fail horizontal line test. They don't technically have inverse functions, meaning they do have an inverse, but their inverse is not a function. It doesn't have the requirement that each input have a unique output. So the way we overcome this is we restrict the domain of the trig function so that they become one-to-one. So what we mean by that, if you take a look at this, this is the graph of y equals sine x. And as you can see from the red line going through the graph, this is clearly not a one-to-one function. It fails horizontal line tests. And this would be true if I were looking at cosine or tangent or any of our trig functions. None of them are one-to-one. So we're going to do what's called restricting the domain. We are only going to look at a piece of this trig function. Now this piece that we're specifically going to take a look at is going to be the function f of x equals sine x between the x values of negative pi over 2 to positive pi over 2. So that's about here to here. This is the piece of the graph that we're going to take a look at. Now there's a few good reasons to choose this particular piece. Notice that if you only look from negative pi over 2 to pi over 2, this will allow us to talk about both negative function values and positive function values. Sine x is negative between negative pi over 2 and 0, and it's positive between 0 and pi over 2. Also, we just kind of keep it close to a value of 0. It tends to make our numbers a little bit easier to deal with. This is what it looks like if you just look at the graph of y equals sine x between negative pi over 2 and pi over 2. So the inverse function of the restricted sine function does exist. The way we write it is either sine with a -1 in the superscript, that's read sine inverse, or arcsine. These mean the same thing. It is called the inverse sine function or the arcsine function. You'll see them both used interchangeably. They mean the same thing. And in general, since the definition of an inverse function says that if you input x into an inverse function and get out y, that only happens if and only if when you input y into the original function you output x. Because of that, we know that if the sine inverse of x equals y, if and only if the sine of y equals x. So I want you to keep an eye on the inputs and outputs of these things and what this means. Let's concentrate on the right side of this for a little bit, the sine of y equals x, because we're a little more familiar with our trig functions than we are with our inverse trig functions. When you talk about the sine of y equals x, and let me give you a specific example. Let's say we're talking about the sine of, let's pick pi over 4. Hopefully this is something you know off the top of your head. This is a part of our unit circle. We do expect you to have that memorized. So, for example, we know that the sine of pi over 4 is the square root of 2 over 2. Watch your inputs and your outputs. When we talk about pi over 4, your input here is an angle, and your output is a ratio. Specifically, because this is a sine function, that happens to be the ratio of y over r. That's the y value, which is root 2 over the radius of 1, which is in our unit circle. So when you're talking about a trig function, you input an angle, you output a ratio, which means when you switch over to talking about an inverse trig function, your input is the ratio, your output is your angle. And that's important to keep in mind when we look at examples for these. So if we were to look at the example and we were asked to evaluate the sine inverse of 1/2, what this is specifically asking us is 1/2 is a ratio, because this is a sine inverse function. That is the ratio of the y value to the radius. But it's usually helpful to think of that as the y value is 1/2 and the radius is 1 in our unit circle. In other words, for what theta, for what angle does the sine of that angle equal 1/2? That's what this question asks us. So we think about our unit circle. One of our angles on our unit circle has a sine of 1/2. And if you think back to unit circle, that's pi over 6. And again, this is something that we expect you to have memorized for unit circle. But if you think about it, there are a lot of angles that have a sine of 1/2. I mean, the sine of 5 pi over 6 is also 1/2. And oh yeah, by the way, the sine of 13 pi over 6 is also 1/2. So why specifically are we focusing and saying, nope, the answer, when you ask for the sine inverse of 1/2, the answer is pi over 6. That's where these restrictions come in. The answer you should be giving back should be an angle in between negative pi over 2 and pi over 2. Neither of these meet that requirement. So that's why we're specifically picking pi over 6. Let's look at a more complicated example. This one is going to ask us to find the tangent of the arcsine of 1/3. Now the other way to look at this, or be asked this, is to say tangent of sine inverse of 1/3. These are the same question. Remember, inverse sine and arcsine are the same thing. So this is different than the previous example for a couple of reasons. The first of which is this isn't just an inverse trig function. This is a composition. This is an inverse trig function with its own input that is then put inside a trig function, specifically a tangent function. So this is actually a two-parter. We need to talk about the sine inverse of 1/3 and then worry about what the tangent of that is. So we're going to work inside out on this. So since we're going to take the tangent of the thing that I just circled in purple, what is inside that purple circle needs to be an angle, because remember the input for your regular trig functions are angles. So I'm going to call it theta. That's traditional. So I'm just going to call that theta for the moment. So the first question we want to answer is the sine inverse of 1/3 equals what? And again, we'll call it theta. So the sine inverse of 1/3 equals something, which means the other way we can ask this question is that the sine of what angle equals 1/3. Okay, this is because these are inverses. So this part of it is pretty much like the example we just did. We're looking for the sine of an angle to be 1/3. The other difference between this one and the previous problem is 1/3. That's not something we have on unit circle. It's not like 1/2 or square root of 3 over 2 or square root of 2 over 2. Those are all unit circle values. 1/3 doesn't appear on our unit circle. So we're going to switch off to triangles. And as long as you're working with acute angles, triangles will work. And we know we're working with an acute angle because theta has to be between negative pi over 2 and pi over 2. So I have this angle here, theta. And I know that the sine of this angle is 1/3. And since we're doing triangles, we can go back to SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we know that for this angle, its sine, its opposite over hypotenuse, is 1. Here's the opposite side. And the hypotenuse will be 3. What that allows me to do is figure out, okay, well, what does this side equal? Using Pythagorean theorem. So we know that x squared plus 1 squared has to equal 3 squared by Pythagorean theorem, which says x squared is 8, which means that x equals the square root of 8, which is 2 square root 2. Technically that's plus or minus, but because we're dealing with the side of a triangle, we're going to go ahead and leave it positive. So the length of this side is 2 square root 2. Okay, so that's a great start. We still don't know what the angle is. We don't know a value either in radians or degrees of this theta angle. But keep in mind, that's not actually technically what I'm looking for. I'm not actually looking for theta. What I'm looking for is the tangent of theta, if you look back to my original problem. I'm looking for the tangent of that angle. And remember, tangent in a triangle is opposite over adjacent, which tells me that I'm going to be able to read straight off of this triangle that the tangent of that particular angle is opposite 1 over adjacent, which is 2 square root 2. And if you rationalize denominator, that's going to be, what, root 2 over 4? So that's the tangent of that angle. But remember, that angle is defined to be the sine inverse of 1/3. So in other words, the tangent of sine inverse of 1/3 is in fact the square root of 2 over 4. And that's our answer. And notice a couple of things. One, we still don't know what theta was. We don't know the measurement of that angle, other than we know it's between negative pi over 2 and pi over 2. But frankly, we don't need to know. We didn't need theta in order to answer this question because of the fact that our original question was a composition. Also notice that when you apply both a trig function and an inverse trig function to a value, notice that as a result in your answer, there are neither trig functions nor inverse trig functions that remain. That should always be true. When you're presented with a question that applies both a trig function and an inverse trig function to some input, you should be able to get your answer to have neither of those when you're done. So since we're talking about inverse functions, we want to talk about cancellation equations, how to undo the application of, let's say, a sine x or a sine inverse x. So when we talk about sine inverse of sine x, notice since those are inverses of each other, whatever the input is will be the same as the output as long as that x stays in between negative pi over 2 and pi over 2. If you reverse the order, meaning you take x, input it into inverse sine, and take the result and plug it into a sine function, that will also just give you x when you're done, but this is for x in between negative 1 and 1. Now that difference comes in because of the order. In the first cancellation equation, you're first inputting into the sine function. And remember, we restricted the sine function to have a domain between negative pi over 2 and pi over 2. In general, the domain of a sine function is all real numbers. But because we're also using an inverse sine function, we need to restrict it to negative pi over 2 to pi over 2. Whereas in the second cancellation equation, x is first being inputted into the inverse trig function, and the domain of that was negative 1 to 1. And if you don't remember that from the previous slide, take a look at this one. So here was our y equals sine x that we restricted from negative pi over 2 to pi over 2. So its range went from negative 1 to positive 1. Now remember, when you're dealing with inverse functions, the domain and the ranges switch. So for the inverse sine function, its domain goes negative 1 to 1, and its range goes negative pi over 2 to pi over 2. And the way that we've obtained the graph of the inverse sine function is by reflecting it over the line y equals x. So of course, inverse sine is not the only inverse trig function we deal with. All of our trig function have inverses. So for example, the inverse cosine function, it's handled very similarly. If you look at the graph of a cosine function, it's not 1 to 1. So we need to restrict its domain so that we get a 1 to 1 function. But notice this domain restriction is different. This one doesn't go negative pi over 2 to positive pi over 2. The domain restriction for f of x equals cosine x goes from 0 to pi instead. And if you think about what this graph looks like, it should make sense why that we couldn't restrict it from negative pi over 2 to pi over 2. Let me draw this graph in. Notice if I had gone negative pi over 2 to pi over 2, what sign, S-I-G-N, is the cosine function always on that interval? Well, it's always positive, and we need to be able to restrict this in a place where we would have both a positive cosine function and a negative cosine function. So that's why you'll always see a difference in these domain restrictions. Once we notice the difference in the domain restrictions, it works pretty much the same way. If you're looking at your cosine function where its input is y, that's the angle, and the output is x, that's the ratio. When you look at the inverse cosine function, the input is the ratio, the output is the angle. It has similar cancellation equations. When you apply both inverse cosine and cosine to some input in either order, you should get that same input back. The difference is going to be the x's that you're allowed to input based on order. Same idea as the inverse sine function. And here's the graph of the inverse cosine function. Notice its domain also goes negative 1 to 1, but its range goes 0 to pi instead of negative pi over 2 to pi over 2. And again, the graph is using cosine x and reflecting it over the line y equals x. If we want to take a look at tangent, its domain restriction also goes negative pi over 2 to pi over 2, just like the sine function, because notice that will take on both negative values and positive values on that interval. And then also this one makes sense because tangent has vertical asymptotes at negative pi over 2, pi over 2, 3 pi over 2, etc. So if we only look at the tangent x function in between negative pi over 2 and pi over 2, notice it is 1 to 1. It passes horizontal line test. And so we can talk about its inverse tangent function. We have similar domain restrictions for cosecant inverse, secant inverse, and cotangent inverse. The reason we kind of leave these off on the side is twofold. One, these are much less used. It's not that we don't use them, we just use them a lot less often. And two, these domain restrictions that we put on the trig functions to force these to be 1 to 1, they have a tendency to be book specific. So these are the ones specific for your book. But if you were to switch to a different calculus book or look these up online, there is a likelihood that these would have different domain restrictions. So we tend to talk about these lightly. We will be using them a bit, but we will use sine inverse, cosine inverse, and tangent inverse far more often. And that's our review of inverse trig functions.